or a cron job or something just to start it up, right? Thanks. All right, so we be recording now. So PS2 is posted for you guys, dealing with pointers. It's due a week from Friday. Looks like PS1 majority of you have actually turned it in already, which is awesome. It's due tomorrow. We extended the deadline out a couple of days just to get everyone up to speed on GitLab and so on. But it looks like most of you figured that out, which is awesome. So there is Sanjina. There is, like, it's too small. Sajna? Sorry, I'm not pronouncing your name correctly. So there is an exam next week. Think of it as a big quiz. So we're talking like, 20, 25 questions, 20 questions maybe, multiple choice. You're going to do it on Gradescope, and it's just going to be stuff that we've covered essentially through this lecture. We'll actually finish this lecture up on Tuesday next week, and I'll post the exam probably that night. And the way the exam works is that it's open for a 26-hour period. And when you open up the exam on Gradescope, you got 30 or 40 minutes to take it. It's timed. And when your time is up, you're done with the exam. So choose what time of day you want to take the exam, open it up, and from then you've got 30, 40, whatever we decide, minutes to take the exam. And as I said, it's all multiple choice. And somebody asked if it would be like automatically graded. It is, and I'm trying to remember if you see that grade immediately. I might have to publish the grades first before you see the grade. But in any case, you'll see them within a day or so, probably less than a day. Filling in code via MCQs. What's an MCQ, Krish? He's not going to tell me. A what? Oh, multiple choice question. Oh, you guys and your lingo these days. Oh, you kids. Yeah, so I know. And in other courses I teach, programming courses, like in 412, there aren't any exams or quizzes. It's all code. And even the lectures, there's no slides. We just talk code all day long, every day, and I grade you on your code. Here I've got to do something to give you some sort of exam or / quiz score, so that's what it is. Can we get an example? Not really. I mean, like it'll be things like, we're talking about scanf today. Like, what's this parameter used for in scanf or some stuff like that. And I'll give you the answers. You guys just got to choose one. I wouldn't worry too much about it. I mean, it's open book, right? And you'll have a compiler in front of you too. So everyone should get 100 on it. It's kind of silly to give exams in COVID land. Like, what's the point, right? But hey, that's what we got to do. What else do we briefly go over? Yeah, I guess that's it. All right. If any of you are still having trouble like figuring out how to get stuff up to GitLab or submit on Gradescope, just hit up your TF. That's what they're there for. I'm around a little bit, but I'm pretty busy. And those guys are, they work 20 hours a week or something on the course. So I got 2 of them. So use their time. They should be able to figure it out for you. I mean, they're PhD students, so you'd think they'd know a thing or two, but you never know, right? Actually, our guys are awesome. Will and Will, they're pretty amazing. And Devin, if you're having Docker issues. And Will Frazier runs Windows. So one of the TFs runs Windows. If you're having a Windows issue, hit him up for sure. All righty then. Any questions before we go on? Oh, the other thing I mentioned is that like in a week or so, we're finally going to get past this kind of elementary stuff. Like, this is just really basic coding stuff. Like, I wish I didn't have to teach it. It'd be nice just to tell you guys, pick up some C on the side so we can talk about the real thing. The course is computer systems. So what we really want to do is, examine like, what is the structure of memory? What does a process look like when it's running? Like, what are the values in its headers? How do they use registers and so on? There's a lot of system level stuff we want to talk about. We can't really until we have this language, this C. We're going to use C to explore those things. So I guess all that to say, if any of you are bored, like it gets really interesting in about a week and a half or so when we start digging into some of the really cool stuff. The C stuff is, it's unfortunate we have to teach it, but you guys don't see C anywhere else, and that's kind of what you need for this kind of course. So there you go. All right. I should remind you also that the deadline to drop without a W, I think, is March something, March 5th or 8th or something like that. So if you're wildly confused at this point, this was the simple stuff, and it gets really complicated pretty quickly as we move into the second half of the course. So just think about that. Just saying, I can't tell you what to do, but something to think about, right? All right, here we go. Oh, and the other thing was PS1. So PS1's due tomorrow. Most of them are in already, so we'll start grading them. You won't see those grades till they're released. But what I want is for you guys to get some feedback on PS1 to inform your work on PS2, because there's going to be stuff we ding you on guaranteed in PS1 that you'll want to make sure you pay attention to in PS2 and going forward. For example, guaranteed I'm going to take a couple of points off, not a lot, like 2 or 3 overall. I'll take a couple of points off if I see single character variable names. If there's an I or a J or a K or an A or a B somewhere in your variables, you're going to get a couple of points off. Not for each one, just once. And the reason that I don't tell you that ahead of time is that I want you to see the points being taken and get pissed. Because when you're angry, like you remember it the next time. If I just told you, it'd be like, oh, whatever. But now you're pissed off at me. It's like, oh, by God, I'm going to show him. And you'll have 40 character variable names going forward. Tell me what it is. If it's a counter variable, name it counter. If it's holding, an address, name it address. No IJKs, they're all right out. And I know, because somebody brought this up in A1, it's like, well, that's every course I've ever taken uses I and J and K and so on. And the book is full of that. I'm here to tell you that the people teaching the courses, most of them are academics. They've never worked actually in industry. I've worked in industry, and if I wrote code with I's and J's and K's and so on, I get called on the carpet because somebody's got to maintain that code. And if I'm 600 lines deep in your code and I run across a K somewhere, what the hell's K mean? I don't know. I'm gonna have to go find out. I got to go find the definition and see if I can puzzle out what you meant by K. If you said size of the array, well, by God, I bet it's the size of the array, and I can just keep going. So it's a readability and maintainability issue. In industry, if you're writing code that we can't read, like it's unmaintainable, like you're not gonna have a job for long because you're wasting our time. So here, no. Can we use IJK in loops? No. What did I just say? No I, no J, no K, anywhere, nowhere. It's like, nope. That one. If you're in a loop and you need a counter, call it counter. Should we, Olivia's like, should we resubmit our homework? Actually, you're welcome to. It's not due till Friday. If you resubmit PS1, be aware that there's so many freaking tools. GradeScope just takes a snapshot when you do a submit. So if you're submitting your stuff on GradeScope, it takes a snapshot of your branch. If you then go and change the branch, that's not a live connection, so it's not going to be updated on GradeScope. You have to actually resubmit it on GradeScope, which is fine. You can resubmit up to the deadline, which I think is Friday midnight, something like that. Nowhere. Kid commit dash fix. Yes. Sweet. Great. That was all the questions there. It's just one of those, like the IJK thing, single character variables. It's just one of those things that's going to save your butt later on. And you need to learn it now. Yeah. Yeah. So the question was kind of the workflow around submitting stuff. So the workflow is you work in CLion, right? And CLion's plugged into Git. Yeah, mine is. So CLion is working on a local Git repo. When you do a commit, you're really committing it locally. You then have to do a push. The push pushes it up to GitLab. So that's your sort of remote storage is GitLab. That only happens when you do a push. So if I change some stuff here, I need to save my file, of course, but I also need to do a commit on that file and then push it up so that GitLab has the most recent version. Then when I go to grade scope, it asks you to log into GitLab and asks you what branch you're submitting. It then goes and reads that stuff off of GitLab and pulls it into grade scope. That's the round trip. Yeah, sure. And again, it's only a snapshot. So if you change something on the GitLab side, grade scope is not going to see it until you resubmit. Can we have access to discussion recordings? You know, Julie, the short version of the answer is, I guess we're not recording all of them. I don't think it's appropriate to record discussion sections not led by a TF. So the CAs, they're doing great work. It's just not appropriate to put that out as instructional material. So really, it's just the TF. Yeah, sure, I'll do it. I'm hesitating because I'm just hesitating, because the discussion sections sometimes are really focused on helping one individual person. I guess that's useful. I do have recordings in the past week or so, and I'll put those up for you, Julie. And if I don't, remind me. All right, what else? Yeah, sure. Nothing else, sweet. Let's move on to strings. Dip. Where's my, here it is. There we go. Strings. All right. No one laughed at the dad joke in A1. The dad joke is that strings are defined with quotes, and so the title of the talk is strings. It's a self-referential joke. All right, so the thing about strings is there are no strings. There's no such thing as a string in C. It's not defined anywhere. There's a string library for sure, but the actual data type string doesn't exist. Most languages are like that. They treat strings as special cases of other kinds of variables, and that's the case in C also. So in C, it's really a special case of an array. It's an array that happens to have a terminating null character. So for example, here I've got two arrays, just chars, T-E-S-T. That's just an array of characters. Its length is 5. If I instead store that as a string, what I get in a string is T-E-S-T, and then this terminating null character. It's the null character that tells the runtime where the end of the string is. So for example, if you do a printf or puts or something, fputs, which we'll see in a sec, I'm printing something, right? And I give it a variable name, print a string. Well, what's in a string? What's the variable a string holding? It's the address of the first character, right? So arrays, in this case, it's actually all arrays. The variable itself holds the address of the first item in the array, in this case, the first character. So if I'm printing something out and tell it print a string, the array, it will go to that first address and print the T, and then it goes to the E, and then the S, and then the T. It's looking for the null. It just keeps going until it sees a null character. In fact, I wonder if I could simulate that. I'm not gonna try. If we print out just chars and like treat it as a string, it isn't a string. There's no null terminating character there at all. It's just 5 characters. And so the print subsystem will start at the T, E-S-T, and then just keep going until it finds a null. Who knows where the next null is? It's just some random value in memory at that point. It's not really terminating my string. It's just, 100 bytes later, oh, there's a null, great. We'll stop printing there. So it really is that special character, that null on the end, that identifies it as a string instead of just a bunch of characters. We'll use the word string, of course, because it's a handy abstraction. But really what's happening under the hood is it's a character array with a terminating null in the last position, which means if we're dealing with strings, like this thing, TEST is 5 chars, right? 1, 2, 3, 4, 5. I'm sorry, it's 4 chars. So I'm a professor. I never was good at math. 1, 2, 3, 4. TEST is 4 characters, but the storage for it is 5 bytes. I've got to have 1 byte for each of the characters and a byte for the terminating null. And that'll come back and bite you at some point. You'll forget that the string has a terminating null. You'll take the size of something or allocate memory for it, and you won't have enough memory. And in which case, you that memory, the byte next to it, it'll overwrite for sure. It'll stick the null in the next byte, but that's not what you intended, probably. Is that a 0? Oh, it's a 0. \0. It's a null. There are some nice things about strings. Like if we're talking about the string abstraction, there are some things that C does for us, which is shocking because normally C does diddly squat for us, right? We have to do everything by hand in C. Well, there's one thing it does for us. If we do this, we say char foo, and notice I say it's a character array, right? So I've got a character array foo. This is a string. It actually builds a proper string for me in that array. So I'll end up with, I don't know how many characters that is, 9 or 12 or something. I'll end up with a 12 character array, a terminating null on the end. It sticks the null on for me. It's like, who is this function, right? Like, is this really C? But it does the right thing for you. And you end up with foo pointing to the T, and then a terminating null that C for you. So that's a nice feature, I think. Like, we don't have to manually stick those terminators in, which is great. A downside is a lot of times we don't know what size string we need. Like, somebody's typing something in the keyboard, standard in, and can we predict how long that string is going to be? Probably not. But we still need some place to put it, right? Like, scanf is expecting the address of some place to put that string in, the string of characters. Like, you just have to guess. Like, here, I've got some input as a string, an array of 50. Is that big enough? Yeah, maybe it is. Maybe it's not. I just don't know. Which means that we have to do testing, right? So if I say, hey, it's a 50 character buffer, and somebody types 60 characters, I need to know that, which means I need to go and look at the input and make sure that it really was 50 characters and not 60. I have to do some work to test to make sure I'm not overwriting that buffer. Let's make sure I didn't miss any questions. Is there a difference between the basic array and the one with the null in it? Not really, it's just an array, and array math works on it. So if I have foo, for example, that's the address of the first character. Foo plus 1 is the H, foo plus 2 is the I, and so on. So it knows about chars and so on. And in fact, the null, that \0 is just a character. It's just a 0, character. All right. So we did this, right? Actually, let's try that. Let's just copy that, pop over here, and some other stuff we were playing with. We'll get there. All right, so I've got an input buffer called sum input. I'm going to use scanf with the address of that. It's going to read in a string for me, right? So let's build that, save it, do a build, and we'll run it. So it's waiting for some input. This is a test. And let's go look at, it's not actually do anything, is it? Yeah, thanks. I meant to debug it. Debug. This is a test, is a test. And let's go look at some input to see what's in there. So here's some input. What we've got is this. What happened to the others? What happened to is a test? I had plenty of room, right? Tons of room. There's a 50 character buffer. What happened? Nobody knows. What had happened was scanf is not your friend. Don't trust a scanf with anything, especially money. Scanf is probably one of the worst written functions in the language. It's just awful. Only this is there because scanf sees the space and assumes you're done and just like stops. It just stops when it sees a space, which is like, oh, really? Yeah, it's a space, Edwin. As awful as VS Code. Well, I can't rag too much on VS Code. Actually, you can take that two ways, right? That's all inflection. I can't rag too much on VS Code. Means Yeah, I probably shouldn't say anything. I can't rag too much on VS Code means I haven't ragged enough. English is so weird. So scanf has some really bizarre behaviors, like stopping on spaces. If it sees a space, it just, I'm done. Thank God, that was a really short string. We're all done here. I'll put that into memory and move on, right? You can explain to scanf, no, that's not what I really mean. We're talking a lot of code to make that work. There's no bounds checking. There's no bounds checking. Scanf will very happily write right past the end of your array in memory, which means that we've got to do the bounds checking ourselves. We've got to make sure that the input value doesn't exceed the size of the storage space. But how do we do that? Because scanf just does it. So that's an issue, right? Scanf, probably if you look at the list of applications that have buffer overflow issues, I bet scanf maps to almost all of them, because if I've got input from somewhere outside of my program, somebody's typing something in, I'm reading something from a file or from a network or something, and I'm using scanf to do it, and I've got a 20 character buffer and somebody sends me 4,000 bytes, I'm going to have 4,000 bytes of whatever they sent sitting in memory, because scanf will just happily copy it all into memory for me. And what if that's malicious code that can be jumped into, and now it's going to execute with the privileges of my program? That's a buffer overflow attack, and one every month. They're really, really common still. It's actually one reason that they took this stuff out of Java, is because it's so prone to error. It's just not even in Java. They said, oh, let's get rid of it. So especially for strings, scanf is just really, really weird. So I'm here to tell you it's the last time you're going to use scanf. And I know the book uses scanf for everything, and I know this course has been taught in scanf for years now. Not anymore. It's my course now, and we're using fgets and fputs. And the reason is that these two functions, so get and put, basically get and put a string, they handle things much more gracefully. For example, fgets has a required parameter, which is the size of the buffer, and it won't let you overwrite it. So if I have an 8-character buffer using fgets, and somebody types in 4,000 bytes, they only get 8 bytes of that in memory, because I told fgets how big the buffer was. So it does a lot, and it handles spaces, special characters, does all sorts of wonderful things for us. Not that it's perfect. It's got issues too, it's like, it's a trade-off. It's like dating, it's like, love going out, but wow, all these issues. And there's somebody else like, still issues. Like, do I got to trade them off? Like, which one am I going to go, right? Yeah, so it still has issues. Let's go play with this. Let's throw this over here. Stop this puppy. We'll write this in. Oops, I need something. What am I missing? I'm missing fget standard in. Like, where are these things? Let's go find out. So let's go import it, and it's going to be in fgets it's an IO, right? It's input output, so it's going to be a standard IO. And that's also where standard in and standard out are defined, so that was handy. All right, let's do this. Fputs, it's going to print it. Yeah, that's fine. I'm going to just go look at foo. Let's build this. Really build it. Thank you. I've discovered, I don't know about you guys, I've discovered sometimes I have to hit the build twice for it to like really build. I don't know why. I guess I could also go to build and just say rebuild project. All right, what are the 3 things for fgets? Well, let's talk about them. This is waiting for some input. This is a test. This is the test. It's Italian. Here we go. You didn't know this is in a different language, right? And return. F you. I forgot to debug it. Sajana, we'll get to you in a sec. This is a return. There's our breakpoint. Let's go look at foo. Here's foo. What's in foo? Foo has this is a test, and that's it. So that was with a buffer of 25, right? So I've got basically 25 bytes from here, from that 74 on the left here. I got 25 bytes assigned to that. Let's go make it smaller. Let's make it 5. Save it, rebuild it. Build me, debug me. And this is a test. This is a test. Now what's in foo? Foo's got just TIS space. TIS space. Where's my I? Oh, it's a null. So it's TIS space and then the terminating null are the 5 characters in the buffer. But it didn't let me overwrite it. It stopped. It truncated the input as it was writing it into memory up to max buffer size. That will save you from at least that buffer overrun. There are tons of ways to screw yourself up with a buffer overrun, but this one isn't one of them now. Scanf for sure it will. fgets, fputs, they work in a cleaner fashion. They'll save you from that problem. So Sanjna asked, what are the 3 values here for fgets? You can kind of puzzle them out, right? So I'm doing, this is the equivalent of a scanf. So I need to know where am I putting it? I'm going to put it in this array called foo. Here's the second parameter that's going to save you. What's the max size of the buffer? Like how many bytes can I write before I have to stop? We define that as 5. So the second parameter is the max size. And then standard in is just a console. So in C and in Unix-based systems, everything is a file. Like every single like system object is treated as a file. And so most of the things we do with logs, like all that stuff, network stuff, it's all a file. All the operations look really similar. And those things we say are streams. So I have a stream coming in from a file, a stream of characters. I've got a stream of bytes coming in from a network. I've got a stream coming in from a console as somebody's typing, or I'm outputting a stream to the console. So standard in and standard out are defined out of the box. Typically standard in and standard out are the same, and they're defined as the attached terminal. So whatever console I have open when I'm running this process, that terminal is attached to the process, and that's my standard in and standard out. You can change them if you want to. I can redefine where standard in and standard out point. It's not common, but let's say I've got a batch job running and my input is not the console. I can redefine standard in to read commands from somewhere else if I have to. Just because standard is just a pointer, really. It's just pointing to some structure in memory that happens to map to the console buffer. I can map it to somewhere else if I need to. The third one you're going to see is, so you'll commonly see standard in, standard out, and standard error is the third one you'll run into a lot. Standard error is just as you think, it's where error messages go, and we often point that to a log file somewhere. Right, so they can point to anything in memory. Maybe the thing that standard error is pointing to is the header for a file. And because they're all streams, I can basically do anything I want with the console, with a file, with a network connection. They all look the same. All right, sweet. Yeah, I just mistyped it. So if we try to input more than 24 characters, it truncates, which is exactly what we want it to do. Scanf versus fget. So now here's the trade-offs, right? So scanf, the F in scanf stands for format. I can define the format of the things that I'm reading in from the console. Fgets, the F stands for file. So there's no format there. Like if I'm typing in integers or floats or like whatever, it's like it just treats it as a string. That's what the S stands for. It's reading in strings. And so if I'm typing in things that are supposed to be numbers, I'm going to have to parse them out manually. So I'll have to go in and collect things out of that input stream and match them to the appropriate type. It's a trade-off, right? Is there any clean way to do it? I don't know. What we end up doing is using this function called stirtoc. This guy. So stirtoc handles that parsing for us. There's no real format parsing on the input side on fgets. So we use strtoke to do the parsing for us. I think I said that twice now. Here's what strtoke looks like. All right, so this is just splitting a string. Most languages have a split operator somewhere, like TypeScript, for example, or I teach TypeScript in 412. Java, I think, has a split on a string. You can call dot split on a string object, give it the delimiter, and it'll return of the individual items from the delimited values. Not so much in C, kind of, but not really. We have to write it ourselves. Let's talk about what this does. Like that ever happens on ComF. Stop. Build. Oh, good. All right, let's talk about this code. This one's pretty short, right? So I'm doing a couple of different things here. One is, notice I'm not defining the size of this. This is just a character pointer called token. What's going to happen is strtoke is going to read a string for us. We're going to tell it what a delimiter is. It's like here, we said the delimiter is a comma. There it is, a comma. So I've got this name, address, phone, separated by commas. The delimiter is the comma. So what I'm telling it is, go and look at input and split this on the commas. So I should end up with name, address, phone as separate items in this buffer. I don't know how long they are. And so I can't really, that was funny. I can't really, like here, this token, I can't really give that a size because who knows what size the token is? I just don't know. I gotta fix that. And so I just give it a pointer. And one nice thing is, I'm gonna mute everybody here. Mute. I muted everybody. I can't remember how to do it from here. I just won't worry about it. All right, so the token itself, like I don't know how big the token is. Name is 4 characters, address is 6 or 7 characters, phone is 5 characters. Like they're varying sizes, right? And so I can't really give token a size for that. But what strtoke does is it looks at the size of the thing before the delimiter, and then it just does the right thing. So it builds the string in memory, essentially. Token, that character pointer, is still going to point to the first character, but strtoke will read the characters up to the delimiter and then stick a null at the end. So I don't really need to know what size it is. It's going to look like a string in memory. It's going to be a bunch of characters terminated by a null because it was built that way by strtoke. I know strtoke sounds like something you do at a party. Like, oh, dude, everybody strtoke, let's go. I can't even imagine what that looks like. All right, let's run it. Let's stop it right here so we can take a look and see what's in token. So I've got the name, address, phone, delimiter is a comma. Let's go and run it, debug it rather. Build me, debug me, make me write bad checks. I don't remember why it stopped. Why did you stop? You stopped because you're not the program. This is not the program that you expected. Go away. Build, debug. Do I need a return there? All right. Here we are. So let's take a look at token. How many variables are not available? Really? Can I just see the memory from here? Where are variables not in memory? Hang on. Let me just rebuild the whole project. Build, rebuild project. That looks better. All right, now here we go. You guys have run into that, I'm sure, also, where you change something and the build doesn't change. One thing I do is when it's screwing up like that, I just go to the build menu, choose build and rebuild project. That essentially doesn't make cleans out all the object files, and then it rebuilds all the objects and links them. So that's a way to guarantee that like you're starting from scratch. All right, let's see what's in token. So token has name. Here's the input buffer. Let's look at the input buffer in memory. Do it this way. So there's the input buffer. Oh, isn't that interesting? So what we've got here is, let's go and look at address of token. So there's token. It's got NAME space and then a null. So that's NAME, just NAME, and then a null. And then we've got the space for the rest of the input buffer. What's happening here is strtoke, as I said, has some issues, a little bit of baggage there. One of the issues is it modifies the input string. So when I give it a string to tokenize, it actually cannibalizes the string, consumes it. So at the end of the operation, you don't have the original string anymore. If you need to, you can copy the string, but it's not that simple. Copying a string in C is not this. I can't just say string foo equals bar. That doesn't work. That points to the same place. What you have to do is figure out how long the original string is, go and allocate memory for a new string that's the same size, and then walk through the original string as an array and copy each character into the new memory location, making sure that you handle the terminating null, and then you've copied the string. So there's not actually any copy sort of thing. Actually, I think the string library does that for us, but I've always just done it manually. All right, so what else is happening here? So token view of this, token's got name. Like there was other stuff, right? Address and phone were in that string too. Like why didn't it split? It kind of split, but it only gave me one value. It's kind of useless. Well, that's because of the baggage. Strtoke returns the next token. Not all of the tokens, the next token. It replaces, I mentioned that it replaces the delimiter with nulls. Essentially what strtoke does is when you tell it to look for the next token, it scans across until it finds a null and then reads those characters in as the split value. So name in this case, it was name comma, strtoke replaced the comma with a null and then read to the null. And that was the first string that it read in. That was the first token, and it stuck it into some value for us. Well, to get the rest of them, we need a loop. And what we're going to watch for is when strtoke is at the end of the input string, strtoke will return a null. Before then, it's returning actual values. So we need a little loop that watches strtoke until it returns a null. When it hits the null, now we know we're done, and we can go look at the other stuff. So that's going to look like this. Let me just go grab this because I don't want to type all of that. All right, here's the new program. Is that going to compile? Let's just do a build. Sweet, that built. It looks similar, right? So here's our input buffer. We said it's 20. I just picked 20 out of my hat. In this case, it's a fixed string, so I probably could have given an exact value. 20 just seemed like it fit. Now I'm going to create a new array. And that array is going to hold the tokens. So every time that strtoke sees a token, I'm going to have it stick that token into this array. So at the end, I've got an array of tokens. My original input array is going to be consumed. It's going to have nulls and all sorts of crap that strtoke put in there. It's going to be useless at that point, but I'll have all the tokens here at least. So here's the loop. While token, which is the same thing as saying while token's not null. So as long as token is true, not null, go and grab the next token. So strtoke grabs the next token. And then once it has it, I'm going to place it into that parsed tokens array. Why am I doing plus plus counter here, by the way, instead of counter plus plus? If I did counter plus plus, it would place the new token at the counter location and then increment the counter by 1. If I do plus plus counter, it moves the counter over and then puts the item in the array. So if I have counter plus plus, it's going to overwrite one all the time. Notice also, here I said strtoke on the input buffer. Here I'm saying strtoke null. Like, what does that mean? It's just, I don't know why. I guess it was the best flag they can think of. All that does is to tell strtoke to find the next one. So that's some weird special syntax that somebody was probably, they came back to the lab after a party. I was like, oh no, I got to mark this. How am I going to mark it? I don't know. Null sounds good. I don't know if there's a specific reason for it. I don't. But what it does is tells strtoke to read the next value in the string up to the delimiter. So we need to do two things here. We need to essentially initialize strtoke done here. So that first call tells strtoke where the input buffer is. It tells us what the delimiter is, and it actually does read the first value out of the string, the first token, and then we're going to put it right here in that parsed tokens array. Then we go into the loop, so strtoke knows where it is in the input array. When I say strtoke null and look for a common delimiter, it starts where it's already sitting and then moves forward and then stops. It knows where it is, so when I say strtoke null again, it picks up where it left off, moves to the next one, and so on. So that null just keeps bumping it to the next token until it hits the end of the array and returns a null, and we're out of the loop at that point. So if we debug this one, how does it reference the input then? Jonas, you're not going to like the answer. It's actually on the next slide. I'll tell you in a sec. It's another one of its problems. It's a little baggage. Let's debug this. All right, so now we've got, here's parsed tokens. Make this a little bigger for you guys. So here's the input buffer. And you can see that it replaced each delimiter with a null, right? So it modified the original input. We kind of expected that because I told you I was going to do it. Here's the parsed tokens array, name, address, phone. It's exactly what we wanted. And in this case, it's we gave it 20 as the size, I think, so it did all 20. Did it? No, it stopped. It stopped at the null. This stuff is just junk sitting in memory somewhere. So those are the tokens, name, address, phone, and then the null at the end. But really, it's just name, address, phone that we're interested in. Everyone clear on that so far? I know, it's just like, I always feel so bad teaching C because it's always like, here's another weird thing that C does that no one else does. And it's kind of like, that's why we have to teach C in the beginning, because it's such an odd little language. Like, it's not like Java or TypeScript or something, or Perl or Python, where I can just do high-level abstract stuff. Here I've got to think about every byte and in memory, and what's it doing there, and why is it there, and what's next to it, and like we have to really dig down deep into the hardware and figure all this stuff out. All right, let me go answer Jonas's question. So Jonas's question was, how's it know? Oh, another question. Srita, when it says name, that's still a character array, and everything before it, yes. Yeah. Actually, that's the next slide. And Jonas, I'll get to your question, I promise, after that one. Here's what that array looks like. So here it is sitting in memory, right? So you can see what these are. That's a character array, right? Actually, it's a char pointer. A char pointer is just the address of the N. Here, that char pointer is the address of the A. Here, the char pointer is the address of the P. If we looked at these memory locations, what we'd see is that what's in memory, well, let's go look at it in memory. Can I do it this way? Yeah. So it's N-A-M-E null. A-D-D-R, etc., null at the end of that. So strtoke is putting the nulls in at the end of those tokens for us so they look like strings. And we know that strings are stored in character arrays with a terminating null. So we've got a character array with a terminating null, right? Here's what that structure looks like. it looks like this. And I apologize that I looks like I drew this with a potato. I drew it in lecture an hour ago. That's what the array looks like. So tokens is this thing across the top. That's the tokens array. Each element of the array is the head of another array. So it's a two-dimensional array. Tokens 0. Actually, what do we have in there? Name. Let me just change these to what they should be. N, A, M. Copy that. Copy paste. E, null. And then the next one is over here. Whoops. The next one's over here, right? So that's going to be the A in address. A. I'll put one more in. D. And so on. Copy that. Whoops. Copy that line. Copy paste and stick it here. Oh, it kind of looks like an array, etc. So each array element is itself a character pointer. Each array element is a character pointer, and that character pointer points to the start of the token. And then we can read down to the null to get the full token, because it's a string. In this case, it's a string. So that's going to have NAME. The first item will have ADDRESS, and the second element of that array will have PHONE, each of those terminated by null. Did that answer your question, Sister Rita? Is this parsed tokens or tokens? It's parsed tokens. We called it something else in the other class. So that's the parsed tokens array. Yeah. Can you repeat the difference between the two? Yeah, so the character array itself, the input values was this one. So there's input, right? So input is this. So NAME, ADDRESS, blah, blah, blah. And actually this has already been through stirtoke, so the commas are missing. But that's the input array. It's all of the tokens separated by commas. And then what happens after stirtoke gets done with it, the parsed tokens end up in a character pointer array. The character pointer in each item is the top of another array that also holds a string. That make sense, Satrita? I guess so.
So, sorry.
Yeah, go ahead.
The parsed token array basically just holds addresses, right? It doesn't really hold characters. It just holds addresses of character arrays, so to say, right?
Yeah, so thanks, Janice. The parsed token array is each item is going to hold the address of the first character in a token. So if I wanted to read the second token, I go to parsed token 1. That holds a pointer that's the top of another array, and then I just read that array to null, and then that's my token. That makes sense, Jonas? Christine says it's kind of like a linked list. Yeah, it's very much like a linked list, with which each character kind of, being part of the linked list. Actually, you guys get to do linked lists in here yet again. How many times have you done linked lists now? 2 or 3 times probably. We're gonna do them again in C, just because they're fun. All right, now we get back to Jonas's original question, which was, I can't remember what it was, but I do know the next thing answers it. Oh, how does it keep track? How does stirtoke keep track of where it is in that input buffer? Well, that's an unfortunate thing, and it's that it keeps a static variable. We haven't talked about static variables yet. A static variable is a variable that's shared across the entire program. So there's one copy of it in memory, and I can refer back to that single copy of the variable in all the other parts of my program, but it's shared, right? Which means that stirtoke is not thread safe. If I'm in the middle of a stirtoke operation, like a loop, and then for some reason I switch to another thread, and by the way, we'll be talking about threading at some point in this course, because it's cool. So we're going to switch to another thread. Well, the original stir-toke was in the middle of something. If I start a new stir-toke operation on the second thread, excuse me, it's going to reuse that static variable. And when I go back to the original stir-toke in the other thread, it's going to lose its mind. It will have no idea where it was because there's only one variable keeping track of where we are. We say that's not reentrant or not thread safe. There is a thread safe version called stir-toke R, R for reentrant. I don't use it because I'm not, well, actually, we're going to have to use it at some point when we hit threads because we're going to have to worry about thread safe code. But for now, it's like, it's just one more thing to worry about. And so I just use stir-toke and just assume that I'm not going to restart it anywhere, like simultaneously restart it. So that's the big thing. It's the static variables that it uses to keep track of where it is. And we can get around it sort of with stir-toke R if we need that functionality. But if using stir-toke R, now I'm probably talking about POSIX threads, and I need to load up the POSIX threads library and so on, and there's a bunch of other stuff we have to do. So that's why I kind of avoid it until we actually need it. There is an alternative. There are a couple of actual alternatives. stir-sep is the most popular one. It does all the right stuff, and it's reentrant, like it's fine. It's not part of ANSI C. It's not part of the standard C library. If you use it, like if you go off and grab stir-sep, it's open source. So you can grab the code, everywhere. If you grab it though, it carries GPL licenses on it, the GNU public license, GNU's general public license. And that license stipulates that if you use a GPL piece of code in your code, your entire code base is now under the GPL. And so there is some serious legal restrictions around using stir-sep. So if I needed something like stir-sep and I wanted to be reentrant and yada, 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 make nice and clean, I would go grab stir-sep and then change it just enough that it was different from stir-sep, but did exactly the same thing, and call it my own. And then now it's under my license and I don't have to worry about distribution rights. It's just a weird thing, sorry. All right, how about comparing strings? Let's do this. Copy that. And GPL is a license. It's a common license for open. Aaron asked this. It's a common license for open source projects. It defines how you can use and reuse and distribute code under that license. GPL is one that what's his name? I can't remember. Stallman, Richard Stallman came up with the GPL over at MIT. He's not at MIT anymore. He got tossed out. But before he got tossed out, he came up with the GNU public license, general public license. And it's just a way to license and protect the intellectual rights of open source software writers. There are zillions of licenses you can use. There's an MIT license, it's a BSD license, a modified, all of those. GPL is probably the most restrictive. What are we doing? We're doing this. Did I copy that? Copy that. Stop that. All right, I'm gonna need some stuff here, right? What do I need? I feel the need for speed. Import it from, where is it in strings or something? Standard layout. Looks good. All right, so there's a couple of strings. Let me just rebuild this. Rebuild. What? Yeah, I always forget that. Rebuild. You can rebuild it better, stronger, faster. I got two strings, one lovely day and one lovely day. I got 2 lovely days. If they're the same, it's going to print out equal. If they're different, it's going to print out different. Let us run it, and they are equal. This is not what you think it means. Not what you think it means. What is in foo? Actually, let's do this. Let's break it right there. What's in foo? It's an address, right? Foo is a pointer. It's a character pointer, which means it holds an address. What address does it hold? 400668. What address does bar hold? Another character pointer, 400668. What am I comparing? I'm comparing the pointers. Are the pointers the same is what that asks. Why are they the same? They shouldn't be, right? They're two strings. Why aren't they in two different locations in memory? In fact, if we look here, you'll see there's one location. There's one lovely day, and that's the only place we see it, right? They're the same because it's the compiler optimizing this code for you. We haven't talked a lot about compiler switches. We'll kind of do them. Yeah, Dev, that's kind of it. It's an immutability sort of thing. It notices, and Java does the same thing, right? So it notices that the strings really are identical, and to save space only stores it once, not twice, and gives the pointers the same address. They're both pointing to exactly the same value, the exact same string. It looks to us like they're different, but they're not really. They're and just because the compiler did that for us. There's probably a way to turn that off. We'll have to have like a whole lecture on, God, what a boring lecture that would be. On the 17th compiler switch we'll talk about is, that's not useful. But just to remember, the compiler is doing stuff for you, right? For example, if you write a loop, a for loop, they say, I've got a big ass for loop, it's done lots of stuff. The compiler might look at that and say, you know what? A for loop requires a lot of jumping around in memory. And when I jump in memory, it takes a couple of machine cycles to jump from one location to the next to execute the next instruction. If instead I unwind the loop, let's say it's a loop that goes through 100 times, instead of just having a tight loop that I just jump back and forth 100 times, the compiler might decide it's faster to rewrite the loop code 100 times. So you'll have 100 copies of that loop with differing values in each instance, and it'll just run them top to bottom, because it really is faster to do it that way than to iterate back over that loop, because it takes more time to do the jump than it does just to bump the pointer up one to execute the next instruction. So also, like, it's like, oh, thank you. Somebody else answered a question. We try to be so clever. Like I remember when I first started, as a dev doing software engineering stuff, like I used to spend a lot of time trying to write really clever code. Like I wanted to be really tight and really like cool and all that. I'd spend a day optimizing a loop, not really thinking about, when I do the compiler just does whatever it wants. Like the code that we write, really those are just hints for the compiler. Like here's kind of what we want to do. The compiler knows better than we do. In most cases it does. And it goes and writes its own code in assembly language to match what we told it we wanted to do. So you might spend a day or two or a week, on a piece of code, and then the compiler just unwinds it. Like, why did you spend all that time? So I try to write my code as simply as possible, knowing that I can rely on the compiler to do some optimization for me. And I can adjust the level of optimization also. There's several levels that I can tell the compiler to do. All right, so here's how we really compare things. So that doesn't work. Instead, we use, we just talked about that, strcomp. So string compare is a function, and it takes two strings and really does do the right thing. So if we copy this, copy that, put it over here, stop this. Yeah, let's do that, huh? Import it from string. Oh, and puts us in standard IO, right? God, that's tiny. Standard, whoops, import from standard IO. Sweet. Dip, rebuild it, because I changed a bunch of stuff. Now, using strcomp, I give it those values. So here's foo, here's bar, it's the address of foo, the address of bar. It's going to compare those two strings byte by byte and tell me whether they're equal or not. Those are equal. If we stopped here, we'll see that they're really two different ones. Actually, it's still going to optimize that, and they are going to be equal. But if I change one, rebuild it, now they're different. Does it maintain those? Yeah, it's still going to optimize that. Right? I'm still going to only have one address, unfortunately. But if I do that, now I've got two strings. That'll give me two pointers. BIF. So if we look at foo and bar, we'll see there are different addresses. One's at C8, one's at D8. So one is, 16 bigger than the other one, 16 bytes. If we do it the other way, if we do this, save that, build it. Now we'll just see it in one location. Which is basically what we saw before. They're both sitting at C8. But strcomp, well, I mean, in this case, it's pretty obvious that they're equal because it's exactly the same string. Strcomp is still going to do the right thing. And when they are different, like the very first thing strcomp does is check the length, because if the lengths are different, they clearly aren't the same string, and it'll just bail right from there. But then it just goes byte by byte and does byte by byte comparisons. Actually, you know what it probably does? It would be faster to do an OR on those things, so it probably treats it as one long number, does an OR, and if it gets anything but a 0, it knows that they're different. Yeah.
Okay, so what if you have two exact same strings, like remove the exclamation mark on the first one? So let's say you want to modify one of them. Would it change both of them?
Yeah, the question was, if I'm in this situation, let me just save that and rebuild it. And let's debug it. So they're the same spot, right? C8. So here's foo. Is there a quick way to do that? That's not a really clean way to do it. Maybe we can do it this way. There's pointers into it, right? Can I change the value? Set value. So let me just change that first byte of bar to a B or something. Buff size. I thought it said buzz fizz. Fizzbin. Can't assign. Oh, hated that. But the question was, if I change one programmatically, will the other one change? Yeah, they're exactly the same location of memory. So if I changed bar, foo would change also. Actually, let's just show it. Easy to show, right? Does the compiler optimize algorithms efficiency? That's a great question. It might change the complexity. So if my loop complexity is like order, n squared or something, it might unwind that so it's an order n. Let's do this. I see changing a string is like, oh shit, I gotta change a string. Bar 0 equals x. All right, so I've just changed bar, right? So foo's got one lovely day, bar's got one lovely day, and then I changed the first character of bar to an x. Let's see what it looks like in memories. There you go. Thank you for doing that. Rebuild, debug. All right, so I'm just about to change that. Oh, seg fault. Oh, I don't know why it's seg faulted. The program crashed. Oh, I know why. It's not bar 0. It's really the value at bar 0, right? Can I do it this way? The value at bar. That's going to be the top one, I think. Save that. See if that works. Yeah, let's try that. It crashed again. Sweet. Yeah, it's not liking the way I'm manipulating that value. But yes, if you changed one of them, the other one would change too, because it's exactly the same string in memory.
So then how would you have it so it wouldn't change?
Actually, that's a great question. So the question was, what if I didn't want that behavior? If I really did want foo and bar to be completely separate from one another, you'd have to do it manually. So you'd have to allocate memory for foo, allocate memory for bar. When I do the memory allocation, which we'll start talking about next week, when I do a malloc, it's going to return a pointer to that block of memory. If I do 2 mallocs, it's going to return 2 different pointers, and then I can store the strings at those 2 places. Yeah, so basically you have to do it by hand. Sweet. That's great. I can't even change the value of a string. It's gonna be a great course. All right. Oh, cool. We're just about where we ended at NA1. There is some information coming out of StirComp, so it'll do a lexical analysis for you. It basically is doing an ASCII analysis for you. So if something appears before something and alphabetically in the ASCII table, you'll get a greater than. So S1 greater than S2 means S1 appears first in the ASCII table. Less than means that it appears after that in an alphabetical list. Equal means they're exactly equal. I think that would be like if we were doing, and in fact, I probably will ask you to do this, like do a like a real simple bubble sort or something with strings. Like it would be really easy to just use this comparison, right? So if I'm doing a bubble sort, I'm comparing two values and I'm either swapping them or leaving them in place, depending on what order they should be in. So if one is smaller than the other, I'll probably leave it in place. If one's bigger than the other, I got to swap them. So StirComp would give me that information. Is it bigger or is it smaller? And that's the data you need to do a swap in something like a bubble sort. Other stuff we can do with strings, and these are all in the string library, string.h, lengths, searching, memory operations to change stuff, copying. If I need to copy a string, there's a stir copy will do it for me out of the string library instead of having to do it manually, and so on. So tons and tons of stuff to do with strings. You'll actually have your PS3 assignment will be working with strings, and you'll be digging around in the string library to do stuff. I do just want to mention one thing before we break and before I run out of battery. It's this, and I just stuck it in here because it just reminded me of when I was writing the slides. It reminded me of this. Equals is an assignment operator. So if I do this, if I say if something equals 5, that is always going to be true because the assignment operator always returns true. Always returns true. It's a typo, right? What I really meant was, is something equal 5, which is a logical comparison. This ends up being an assignment, which is true. It's a logic error. This will not crash the program because of that. That's not a syntax error at all. I'm just assigning the value 5 to the variable something, and then it just keeps going. It's a logic error, though, as the program runs. That's not what I expected. Like, that's not what I intended, right? And so it's going to screw up somewhere. To avoid that, always stick the literal on the left side of that comparison. That's a syntax error. If I try to assign something, that's basically saying 5 equals something as an assignment. That's a compile error. The program won't compile, which is preferable, right? You want to know that you made that mistake and go fix it rather than having this not throwing a syntax error and you deploy that code somewhere and the Mars lander doesn't land because you screwed that comparison up. Anyone here, did the little guy land? He was supposed to go down at 1, I think. I hope he did. Yet another Mars lander. And so just like try to get in the habit of when I'm doing a comparison, do it this way. Put the literal on the left. If I screw it up, it's a syntax error. That said, 355, thank you. Oh, that's great. I can go back to the office and watch it. I've coded since the 70s in multiple languages. I've taught programming for 20 something years in multiple languages, and I tell every class this, and yet I still write it if something equals 5. It's just habit, That was the habit I picked up when I first started coding. And even though I try, like after this lecture, I'll go back and I'm going to do it right this time. I'll do your assignments or whatever. It's like 5, equals something. I'll do it the correct version of it. And then in a week, I'm back to writing something equal 5. For you guys, like you're young, like get in the habit of writing the literal first and then the variable you're comparing against. And if you get into that habit, like you don't have to think about it, right? It's just going to save you when you screw something up. There's no hope for me, clearly. It's like I'm just hopeless at this point. All right, so that's where we ended up in A1. That's where we'll end up today. And there's just a couple of more things to talk about strings. So we'll just finish that up on Tuesday next week and then jump into structs. It's going to take us a couple of days to talk about structs, I think. Struct, S-T-R-U-C-T. And apart from that, you have more questions about the assignments. Your best bet is to grab a TF. Second best bet, grab a CA. Third best bet, pop on a Piazza. Try to find me. I'm just really busy. So I really rely on the staff to field questions and then ask me a question if they can't solve it. But that's it for today. Good luck. Look forward to seeing your PS1s, your PS2s next week. Go in peace. Good luck, little lander. See y'all. Stop recording.